Okay.
Good morning, everyone, and welcome to EDP and Applied Mathematics Seminar. It's a pleasure for me to open session 49 of this seminar. Today we have two excellent speakers, George Yin and Vladimir Neves. Introducing George Yin, we have to Professor Roberto Capistrano. Thank you, Roberto. You can start.
Okay, thank you, Juan. Hi, everyone. Good afternoon. Well, it's a pleasure for our seminar to welcome Professor George Yin from the University of Connecticut, US. Okay, Professor Yin will talk about the stochastic problems. Let me tell you a little bit about the Professor Yin. Professor Yin obtained his PhD from Brown University in 1987. After the PhD, Professor Yin went visited a lot of universities like University of Bordeaux, University of Toronto, University of Oxford, University of Melbourne, among others. He is also a distinguished professor at Wayne State University, and since 2020, he has been a full professor at the University of Connecticut. Professor Yin works on control and optimization problems for the stochastic equations, among other topics, of course. Professor Yin has 30 PhD students, more than 450 publications between articles and books. Additionally, he has more than 4,000 citations on MathSciNet and more than 19,000 on the Google School. Okay. Professor Yin is editor in a lot of journals. Also is editor-in-chief of the Science Journal of Control and Optimization. And in 2015, received the Science Fellow Award. Today, Professor will give us this great opportunity to attend his lecture entitled Stochastic Kolmogorov System and Application. Thank you very much, Professor, for this opportunity. You can start, okay?
Thank you, Roberto. Thank you for the invitation. It gave me a great pleasure to give the talk in your institute. I'm really happy to be here to meet many new friends. My special thanks go to Dr. Juan Limaco, who actually made a lot of arrangement. We had a lot of email communications. Thank you. So here is an outline of my talk. I will begin with introduction, and my main or primary objective today is to go through some examples. I realize that many people here are working on partial differential equations, not necessarily in stochastics. So what I'm going to do is probably use some examples to illustrate that. So the first example is the so-called Sar model. And then we'll talk about the functional Kolmogorov system, which is, I'm just going to do a brief introduction. And I don't know if I have the time to do the stochastic chemostat system, the control the system or not, because the time seemed to be a little bit short. So finally, I'll give some remarks, then we'll conclude the talk. So you may wonder, what is a Kolmogorov system and why we want to study that? Actually, that is my main objective today, to talk about those two things. So what is the motivation? Well, the motivation actually comes from a fundamental question in population biology. So the question we wish to answer is, what is the minimal condition? Minimal in the sense of necessary and sufficient condition for long-term persistence of a population or for long-term coexistence of interacting species. So what I'm going to talk about today is actually joint work with some of my colleagues. So Don Wayne was a former student, now a professor at the University of Alabama. New Wen, who just finished this year, joined the University of Rhode Island as an assistant professor. Zhu is a colleague from Vietnam. Professor Zhu is another colleague from Vietnam who actually was the director of the Vietnam Institute of Advanced Study before. So anyway, you may wonder what is Kolmogorov system. So let me begin with the following definition. So here I'm looking at a deterministic equation. So you have an n-dimensional system. So xi dot actually is equal to xit times fi. Fi depends on n variables, x1 through xn. So this system is what we call the Kolmogorov system. Actually, you know, Kolmogorov himself said he has, he's very good mathematician, as everybody knows. He said the foundation of probability theory. But he said he really has a passion in two things. One is biology. One is Russian history. He has more interest on that, those aspects. So in fact, this setup of the Kolmogorov system actually comes from some early work, and later on you will hear that. So actually, Kolmogorov didn't do, he only looked at this problem. The way he set up the problem is two-dimensional system like xi prime is equal to x times f of x comma y, and the y prime is equal to y times g of x comma y, something like that. But it has pretty dramatic impact in the subsequent study. So, but here we are studying the random or stochastic systems. So now I just add the noise W1, or here I use the B1 and B2 as the Brownian motion. So the two Brownian motions can be independent or not. For simplicity, here I put a two-dimensional system, but you can easily generalize that to the higher dimensional system. Now, you can realize that very clearly a very special case would be like a linear case. If you put f and g as a linear thing, then this one is just the so-called geometric Brownian motion. For people who are working on finance, that's the basic model they are all working with. But here we are looking at the non-linear model. So, well, another question I mentioned is why we should study Kolmogorov system. There's a long, list of models we actually coming from here. The very well-known model is like a Latkavatera competitive model or predator-prey models. And here I also mentioned the replicator dynamics, epidemic model, and so on and so forth, tumor immune system model, and so on and so forth. So there are lots of models. Many nonlinear system models actually falls into this category. So now, let me begin with the idea of a growth rate with very simple example, which we teach our undergraduate student in the differential equation class, which is the logistic equation. Now, in this equation, as you can see, R is what we call the growth rate, and K is the so-called intrinsic computation rate. Now, then if you add the noise to it, then what happened? Now you see here I have the R minus K xt dt xt times that. This is the inner form of the Kolmogorov equation. But I also have the noise term built in, so I have this term. Now I'm asking the question, what is the growth rate? So you see now the growth rate is no longer R itself, but it's R minus sigma squared over 2. Now, this actually is a very important factor. In fact, today, if I can get through the basic idea of what is the growth rate, then I really kind of achieved my goal. So you see, this equation, for the deterministic equation, you can solve it by separation of variables. For the stochastic thing, you can also try to solve it. So what happened is that we can study the stability of the system. For the stochastic system, if lambda is less than 0, the population goes extinct. If lambda is greater than 0, the population is persistent. If lambda is equal to 0, that's the more difficult case. This is what we call the null recurrent diffusion in stochastic theory. So in any case, you see the problems are all determined by the growth factor. So now there is a long list of references for us. So I mentioned a number of them, including the original Lotka-Vatera model, the Kermack and the McKendrick model, and you will see that later, and the logistic model, and so on and so forth. And now fast forward, I mentioned some very recent work. Especially, I'd like to mention the work of Benham and the colleagues, Schreiber, Evans, Henning and the colleagues, and so on and so forth. You'll see they have some something to do with what we are going to study in this talk. So for ourselves, we started looking at this in the maybe mid and late 2000. So we look at the two-dimensional system first, and then we look at the corresponding thing for n-dimensional systems with the so-called n patches. And my former student, Wing, together with Henning, actually did a paper in AAP, Annals of Applied Probability, that's they considered the general Kolmogorov diffusions and gave a complete characterization of the system. Now, then we thought, we have this, what about if we have a delay? So now very recently, last year, we actually published the two papers. The two papers settled the matter for functional stochastic differential equations. So here, the main idea we are using is the so-called Dupaire's functional Ito formula. We use the asymptotic coupling, we use dynamic systems approach. You will see some of these ideas later, not all the details. So this picture is a diagram saying, what kind of system we can treat with functional differential equation treated. Actually, we are treating more general systems. All right, so I already mentioned persistence and extinction. So you may wonder, what do we mean by that, especially in the probability setup? So here are the definitions. Roughly speaking, if I'm not reading this, by the way, the subscript X and Y denote the initial conditions. So what we mean here is that we say XT is persistent, stochastically persistent, if it's bounded with a large probability, with probability close to 1. Roughly, that's the idea. Now, likewise, we can define this persistence for Y. If both X and Y are persistent, then we say the system is persistent. So here I'm talking about two-dimensional system. If it's a higher dimensional system, it can be, of course, defined in the same way. Now, so then you will ask, what would be the case? What do we mean by the population is extinct? Say if X is extinct, what we mean by that? We mean as t goes to infinity, X goes to 0. with positive probability. We don't need this to be probability 1, just positive probability. If there is a chance that can go to 0, that's extinct. That's extinction. Likewise for the y component. Now, as I already mentioned, in this talk, the main thing we would like to answer, or the fundamental question is, under what conditions is the system persistent? Okay, if the system is not persistent, so suppose you have 2 species. Now, which one is persistent, which one is extinct? Can you pinpoint that? So that's the basic concern. Now, there have been many studies on the subject. Now, many works concentrate on using Lyapunov function ideas. Naturally, when you study stability, you use a Lyapunov function. But there is a catch. When you are using that, using Lyapunov function, you see, it may not be as sharp as you would like to. The results are not related to the coefficients or the system itself. So what we do with it? Now, in order to show how can we study such system, actually, I'm going to look at one example. As I mentioned, basically today, I'm only going to talk about the examples. So the first example is Slr model. So I couldn't help to bring the picture of Ronald Ross, who actually was a Nobel Prize winner in UK. And he, in fact, was the first Nobel laureate in Britain. And the first Nobel laureate actually was born outside of UK. So he was the eldest son of his family. His father had 10 children, so he was the eldest. He was really a genius because he was good in almost everything. When he was 14, he wrote mathematics books, and he was good in music. He composed some poetry. That he had a wide variety of interests. But his father really wanted him to be a physician. So finally, he followed his father's wish. And then coincidentally, he was the doctor. He was a doctor when the malaria broke out in India. So he was responsible to working in the epidemiology in that regard. So that's basically how he got the Nobel Prize. Now, I would like to say contemporary to Ross, there was another person, Giovanni Grassi. He also worked on malaria. He was more or less on the experimental side. He was the one actually identified the mosquito responsible for the malaria. So there was a kind of big competition between those two who should get the Nobel Prize. I think by now, probably both of them will share the prize, but at the time, there was another person, a mediator named Koch, who actually heavily in favor of Ross. So Ross got the Nobel Prize, but Grassi didn't. This is just some digression. But anyway, building on the research of Ross and Henderson, Kermack and McKendrick actually published the 3 papers in this Slr model. So now those 2 guys, Anderson, Kermack and William McKendrick, they were both Scottish, but they were not truly mathematicians. They were, like physicians and biochemistry, but biochemists. However, they they were very good. They were very good in mathematical modeling. So the SIR stands for susceptible, infected, and removed. So that's the 3 letters stand for. Okay, so there is a class of people who can be infected. There is already infected class, and there is class who got infected and recovered later on, becomes immune forever. Now, this is not like a COVID, because COVID, the person can be reinfected. So there is, there's some other models of the variation of SIR, but I will not talk about that today. So what is the model? The model is actually coming from the deterministic equation. As you can see, it's a nonlinear equation of the form of a Kolmogorov system. Now, alpha, beta, mu, rho, and gamma all have some specific meaning. In fact, for like birth rate per capita, contact rate, death rate, and so on and so forth. So if you have a such system, then what do you do with it? I remember the time when I was a student, Jack Hale, I'm sure everyone heard about him. He was working on ODE and also later on functional differential equation. During our prelim, he asked the question, if you have a 2-dimensional system on a plan, what do you do with it? So the first thing, what do you do is you look at the equilibrium point. So basically you said the right-hand side equal to 0, you solve it to try to find the stationary point. That's basically how people did for this model. So what they found is that, there is a threshold. There is a threshold, lambda d, given by this. If the threshold is less than or equal to 0, then the population tends to disease-free equilibrium. If lambda d is greater than 0, then the population approaches an endemic equilibrium. So that's the conclusion of it. Now, what we are really interested in is the stochastic model. So we add in the noise, B1, B2, B3. So the first thing you look at that is that, why should we have 3 Brownian motions? They seem to come from the same source. Why not just 1 Brownian motion? Yes, you can do that. Then we get the following, looks like a simpler differential equation. However, it turns out this differential equation is more difficult to analyze than the one with different B1, B2, B3. Why? Because this matrix, if I write this in the matrix form, then this matrix would be degenerate. It's not full rank for the diffusion part. Okay, so that's the basic difficulty. Now, what is the main question we wish to answer? The main question we wish to answer is, under what conditions will the population be permanent or persistent, and under what conditions will the disease be extinct? So that's the basic question. So we would like to get something like lambda. Now, the first thing we realized that for the 3 equations that remove the class, we can really remove it because it's not very essential for us to study that. So we look at the 2-dimensional system, S and I. S is the susceptible class, and I is the infected class. Now let's see how we study that. Now, if you look at this, you may ask the question, do we have a unique solution for this system of equation? In fact, we can show there is a unique solution. And also, not only that, but also we know the solution actually lives in the first quadrant. They are non-negative solutions. Now then, so basically you ask the question, what should the corresponding thing like the threshold level be? It turns out in this case, the threshold is related to the Lyapunov exponent. So we'll see how that, or how do we get that? You know, so now let me go back to the system. I'm looking at the first equation. Now, suppose I is very small or I is equal to 0. I can knock out this term. So I have a new equation. It's a reduced equation. Now, this reduced equation is what I read as hat, the equation, hat equation. For the hat equation, hat as, I can say a lot because there is an invariant probability density associated with that by solving the corresponding PDE. Is a so-called forward equation. By solving that forward equation, you can actually get this density. Now, not only that, but also, you know, there is a law of large number holding. If you look at the long run average of the S hat, then you should go to the mean of this gamma distribution, which is alpha over mu. All right, so this is very good. We continue. Basically, we would like to know what is the growth rate. Remember, my very first slides was on logistic model. Over there, we said, you know, for the deterministic model is R. For the stochastic model, it becomes R minus sigma squared over 2. So what about this guy? Now let's see. I claim the threshold is of the following form. Now on the right-hand side, the term, the black terms, those are exactly as in the deterministic setup. Whereas the right term actually is an additional contribution from the noise term. Sigma square, in fact, is the variance of the diffusion part. So I can rewrite that as lambda d. Lambda d is the threshold for the deterministic system. Now, you may wonder what is the lambda coming from, right? Well, this lambda is nothing but the Lyapunov exponent of the infected class IT. So why is that? Well, so basically we do the following. We expand IT. We take a logarithm. We use the Ito formula, we get the first line. Now I have 3 terms. The first 2 terms, the black terms, those are small. This one is, you know, I0 is a constant. So when t is large, this one goes to 0. The second one goes to 0 by law of large number of Brownian motions. Now the last term, the last term I wrote as a blue term. Let's look at that more carefully for the blue term. For the blue term here, I'm using some intuitive idea. This is another proof. When we prove it, we use a very different approach. So now if you look at this integral, you see when I is small, S can be approximated by S hat. So I have this term. So I'm using approximation. Now, then the law of large number tells me the average of this term is alpha times beta over mu. And here I have the rest of the terms. Now, if I put all of them together, you basically get, you know, the Lyapunov exponent of I is a lambda. So this can be rigorously proved by using comparison ideas of the S and the S hat T. It's another one I'm doing here, but this one gives us good intuition. So as a result, if lambda is less than 0, then IT decays exponentially fast. If lambda is greater than 0, IT cannot be small for a long time. So the disease will survive permanently. So that's our first result, basically saying just what I said. If lambda is less than 0, then, you know, the Lyapunov exponent is equal to lambda almost surely. And the S susceptible class converges weakly to the unique invariant probability measure with density F star. F star is the one with the gamma density, as I mentioned before. Now, here is a computation example. We put in some numbers for alpha, beta, mu, rho, gamma, sigma 1, sigma 2, and so on and so forth. So you see, in this case, lambda is less than 0. Now, then the picture on the left-hand side, it shows the picture of S component, the susceptible class. This is what people in finance would call that mean reversion. So basically it tells you there is the invariant measure associated with that. But for the I component, you see it decays very fast to 0. How fast? Exponentially fast. All right, so here I superimpose the solid curve is gamma density, whereas the zigzag stuff is the empirical density associated with that. You see, we have a very good match of that. So when lambda is greater than 0, then we will show that the two-component process, ST and IT, has invariant probability measure in the first quadrant. So now we know that from the early work of Stroop and Warda in 1970s, saying if the diffusion is degenerate, then the invariant measure may have a support which is not the whole space, but only a portion of it. So now the question is, how do we find this support? Now, so here, what we are going to do is we use something coming from a control theory, in fact, geometric control theory. And we verify Hohmander's condition, basically a property of vector field. This condition also known as Reshevsky, Chow, and Hohmander's condition. So basically, we are looking at the vector fields A and B. Those are coming out from our differential equation. This is just, I'm looking at the corresponding Lie bracket. So that tells you the Hohmander's condition says if the set of vectors B, those bracket actually generate the R2 space for every xy in the first quadrant, then the diffusion satisfies the Hohmander's condition. So for us, we are looking at the control system. There is no stochastic here. It's purely deterministic system. We treat phi as a control. And now we are looking at the solution of U and V, two component, where phi is the control, U and V are the initial condition. What we are looking at is the so-called reachable set. Starting from the point UV, we try to find the set, the entire collection of a set, U prime, V prime, belong to the first quadrant, such that we have this condition satisfied, U phi equal to U prime, and V phi equal to V prime. So we can characterize this, and by using this Hohmander's condition, we can show that the corresponding control system has a, the two-component thing has a unique invariant measure. And, the support of the invariant measure, in fact, is given by U to the R's power times V greater than or equal to D star. Well, you may wonder what the D star is. Here I have all the information for that. Okay, so now let me skip that because I think my time is short. So what happens is in the total variation norm, we can show that the convergence take place. The transition probability converges to the invariant measure. But the convergence rate is not exponential It's short of exponential. It's a polynomial. All right. So let me also give you a computation demonstration. So this gives us a particular, example for alpha, beta, mu, rho, and so on and so forth. So I see both components. So this picture shows both S and I are mean reverting. So to say that both have an invariant measure. Now on the left side, this picture shows what is the support of the invariant measure. On the right-hand side, it shows to us the density associated with that. That's basically the first example I'd like to demonstrate. I think I only have, maybe 4 or 5 minutes left. So I think I'll skip the discussion or the remarks here, but go into the next one, which is the stochastic functional Kolmogorov system in a more general way. This is much more difficult to deal with because now I have the differential equation 3.1 given here. But here you see I'm writing down x sub t. What is x sub t? If you studied like Jack Hill's book on functional differential equation, that's the same thing. So the phi sub t, in fact, is what we call the segment function. It belongs to the continuous function space. So here I pinpoint that part. So now what we are looking at, in fact, is infinite dimensional subject rather than finite dimensional subject. So again, we would like to know one, for this general system, one, we will have persistence or permanence. One, we have extinction. Now, how do we actually do that? Well, you see, this is still a long-standing question, like the extinction and the persistence. But now what we have to work with would be, the continuous function space and the boundary interior of the script C and so on and so forth. All right. So what we do, we are still looking at the Lyapunov exponent. So here, if I do the expansion for xit, take one of the I take just like what I did in the previous example for the two-dimensional case. I do the expansion using, the Ito's formula. The right-hand side, I have 3 terms. The first term I can show that goes to 0 pretty fast when t is large. The second term we can show that goes to 0 with probability 1 by using the so-called local martingale convergence theory. It's not just Brownian motion, but some stochastic integral stuff, but you can still show that. So basically that says the last term or the right term actually dominant. So this one is what we are looking at, the Lyapunov exponent. But this one, further, we can rewrite that. So if we denote, we can approximate this by using the average with respect to the measure mu in the following form. Then lambda I mu are precisely the Lyapunov exponent. So there are for the basic idea for the functional stochastic Kolmogorov system. In fact, the proof is much more complicated, long and technical. So let me just go through very quickly the stochastic Chemostat system, this one actually appeared in 1950s and later on studied by many people. So we still want to study, for example, like a persistent and extinction, but in particular, let me mention one example we are interested in is that we would like to control the wastewater management. So for that case, we put in a UTS the control. The problem is to find the optimal control of the problem. What we are looking at is this long run average criteria. The difficulty, however, is that there's a problem of there's a book by the three authors, but they use something. They said you need the two conditions, either near monotone or a stable condition. So basically, here for people who are working on partial differential equations, you see, when we solve a control problem, basically we solve PDEs. So here we have to solve PDEs. Yeah, I think I need to stop. Okay, I will stop.
Professor, sorry, was one participant open the microphone? Sorry, you can keep.
Yeah, it's okay. I will finish in a couple of minutes. So here, our idea is to combine, to separate the region into two parts. In one part, it satisfies the near monotone condition. In the other part, it satisfies the stable condition, and then combine them, so we can find the optimal control. But let me just run over that. Just final remarks. So in this talk, we consider the Kolmogorov system. We illustrate the idea of permanence and extinction, and additional jumps can be built in. And there are many related control optimization and game problems remain to be investigated. So let me just say thank you very much for your attention. And yeah, that's my presentation. I hope I didn't go over the limit of time. We started a couple of minutes.
Professor, you have time if you want to show.
All right, thank you.
Okay, thank you. We have time. Well, 10 minutes. The microphone is open for questions or comments, please. The audience have comments or questions about the talk of Professor George Yin. Well, let me do some curiosity. I'm working PDEs, right? Okay.
Sure.
Well, you work in kind of problems of, for example, models, CRIR models that can study with ODEs, right?
Right.
What's the main point you change for the ODEs to stochastic framework? Do you have some gain? I mean,
yeah. So the main point for using SDE is that in reality there are always noise there. So this is the kind of noise we call environmental noise. In fact, for people working in biology, they consider that there are two different types of noise. One is called the demographical noise. The other one is environmental noise. The one we treat here is the so-called environmental noise. So basically, those are the factors you cannot ignore that perturb the system. So the system parameter may never be the same as truly just the deterministic number, but there's some environmental thing, built in. So you want to take into consideration of that. That's the reason for that.
Okay. Another point is most of these models you can trade with numerical analysis, right? Together with stochastic problems.
Yeah, basically, it's once you have the differential equation, then you can try to numerically solve it or simulate it, get some idea. So for the demonstration, we basically just it's get some ideas, but the asymptotic property we have to prove it. So
okay. Thank you.
So the fundamental question is, if you have a population, will the population survive forever, or the population will die? If you have a disease, is the disease going to be forever endemic, or is going to be extinguished at some point, extinction. So this is the fundamental question. So people basically wondered for a long time, what is the condition needed for the extinction or permanence?
Okay. I mean,
so
yes.
Basically here we are trying to answer that question.
Yeah, I understand that. Perfect. That's a beautiful talk, Professor. It's good because you can see, in fact, what's happened in some points, or maybe in some times in the population, like epidemiology problems or growth the population, something like that. It's very, very good for application, at least. Okay.
Yeah, I agree. Perfect. By the way, the SLR model is also used for social network modeling, for spreading rumors, the susceptible, the infected, and the removed class.
There is a question here of Rafael Lobosco. If this theory have application of financial theory, I mean, economy or something like that. If these there are some application in economy, for example.
I think so. Yes, indeed.
Rafael, he say yes. Sim, ele diz sim, que provavelmente sim, existem aplicações.
Yeah, you can formulate problems under random perturbation in that way. And for one of the simplest model would be the geometric Brownian motion. People use that in finance every day. But in economics also, there are many. So you see, the solution of the process, even with the noise built in, still belong to the first quadrant, non-negative solution. So that fits into many of the economics models.
Ok. Rafael, pode ser aplicado, tem várias possibilidades de ser aplicado isso no mercado financeiro, etc. Do you have some other question? The audience, please, can share with us in the chat or in the microphone. The microphone is open. If not, let's thank you again, Professor George Yin. It was a perfect
thank you
today.
Thank you so much. I very much appreciate, and very nice meeting everybody. So virtually, although virtually. So,
thank you, Professor.
Thank you. Hopefully we can meet in person. Let me stop sharing.
Yeah, I will try to send you a message by email. Maybe we can find some possibility to visit you here in Brazil. I send you a email.
Thank you.
Thank you, Roberto, and thank you a lot, Professor George Yin, for your amazing talk.
Thank you.